The invisible idea that changed everything, Dalton's vision. For most of human history, everything you could touch, see, or feel seemed continuous, unbroken, whole. A rock was just a rock. Water was simply water. But hidden beneath that certainty was a question so simple, it almost felt unimportant. What is everything actually made of? Ancient philosophers guessed wildly, imagining tiny, invisible particles called atoms. But they had no proof, only thought experiments drifting in. Then, in the early 19th century, something changed. John Dalton took that ancient idea and turned it into science, proposing that all matter was built from solid, indivisible atoms, each element defined by its own unique type. It was a bold claim, clean and convincing, and for the first time, it felt like we had uncovered the true building blocks of reality. But there was a problem. Dalton's atoms were perfect, featureless spheres, completely indivisible and eternal, leaving no room for complexity, no room for hidden structure. And yet the world itself hinted at something deeper, something inconsistent with this simplicity. Chemical reactions behaved too precisely, patterns emerged too consistently, and subtle clues began to suggest that these atoms might not be as solid or as final as they seemed. What if the smallest thing we thought we understood wasn't the end of the story at all? Cracks in the model Thomson, Rutherford, Bohr. For a while, Dalton's vision held strong, a simple and satisfying picture of reality built from tiny, solid spheres. But science has a way of testing even the most convincing ideas. And by the late 19th century, strange results began to appear. Experiments with electricity revealed something unexpected. Atoms were not completely indivisible. Thomson discovered the electron, a tiny negatively charged particle hiding within the atom, shattering the idea of solid, uniform spheres. Suddenly, the atom had structure. Thomson imagined it as a soft, positively charged mass with electrons embedded inside, like raisins in a pudding. It explained some things, but not everything. Then came a result so shocking it forced scientists to rethink everything again. Ernest Rutherford fired particles at thin sheets of gold, expecting them to pass straight through. Most did, but a few bounced back as if they had hit something dense and powerful. It was completely unexpected. Rutherford realized the atom was mostly empty space, with a tiny, dense nucleus at its center. The solid atom had collapsed into something almost hollow. But this raised an even bigger problem. If electrons orbited this nucleus like planets, they should lose energy and spiral inward, causing atoms to collapse. Yet atoms clearly existed. Niels Bohr stepped in with a radical idea. Electrons could only exist in specific energy levels, jumping between them without losing energy in between. It was a strange fix, but it worked. Still, beneath these solutions, a deeper question remained unanswered. If each model kept breaking under closer inspection, what was the atom really like? The quantum revolution, where reality breaks down, by the early 20th century, the atom had already been reshaped again and again, each model more complex than the last. But what came next did not just refine our understanding, it completely shattered it. Experiments began to reveal behavior that defied logic itself. Electrons, once thought to be tiny particles orbiting neatly around a nucleus, started acting like waves, spreading out in space instead of existing in one fixed point. This was not just unexpected, it was deeply unsettling. The idea that something could be both a particle and a wave at the same time introduced a level of uncertainty that science had never faced before. Werner Heisenberg formalized this with the uncertainty principle, showing that you could never know both the exact position and momentum of an electron at the same time. In other words, the more precisely you tried to measure reality, the more it slipped away. Erwin Schrödinger took this even further, describing electrons not as objects, but as probability clouds, regions where an electron might exist rather than where it actually is. The atom was no longer a miniature solar system. It was something far stranger, governed by probabilities instead of certainty. And despite how abstract and counterintuitive this sounds, this quantum model is the most accurate description we have. It works with incredible precision, predicting outcomes with astonishing accuracy. Yet it leaves us with a haunting realization. At the deepest level, reality is not solid, not predictable, and not fully understandable. The closer we look, the less certain everything becomes.